based in the Wallon region. It's the south part of Belgium. And we work with spectroscopy dedicated to the agriculture product since around 40 years. And we try to predict new models based on these techniques. My presentation will be in 3 parts. First of all, I will make a small introduction to the mid-infrared spectroscopy. And after that, I will focus on some practical use of mid-infrared and some topics very important to know. And after that, will finish by giving you a concrete development of models that we have developed in GplusE project. Okay. The first part is the introduction to the mid-infrared spectroscopy, and also I will ask about chemometrics. As you know, the spectroscopy is the science to study the interaction between matter and light, and it's based on the electromagnetic radiation. Here it's presented the electromagnetic radiation for the visible part that everybody knows. The electromagnetic spectrum, it's represented here. You have the visible part in the middle, and as you can see, the electromagnetic part covers the radio waves that you use for listen to the radio. But when it's very large waves, and when you decrease the waves, you go directly to the microwaves. After that, it's the infrared part. And after the visible part, it's the ultraviolet part and the X-ray. And to finish, it's the gamma rays. The energy of these waves increase when the waves decrease. We will see more in detail the infrared part, which is very used in some techniques using spectroscopy. But there are also other techniques who use this electromagnetic radiation. Here it's represented some techniques. It's the fluorescence part within the ultraviolet part. But also you have UV visible spectroscopy using the visible part. You have in the infrared what we call the near infrared and also the mid-infrared. It's 2 parts of the infrared, totally different. And also you have the Raman techniques, but I will not speak about that. Here in this presentation, we will work on the mid-infrared. And this technique is based on the interaction between matter and photon. As you know, the covalent bonds share electrons between atoms and in a molecule. And bonds have a length. And this length is unique for each pair of atoms. The bonds act like a spring. A spring is resort in Spanish, ressort in French. And this spring join atoms. And these bonds vibrate at a unique frequency due to the atomic masses and stiffness of the atoms. And what happens when we use the techniques? A photon of exactly the right frequency is absorbed and excites the bonds to a higher vibrational state. And this frequency depends of the bond. Okay? Every bond has its own frequency. And when you apply these techniques, the frequency gives the the qualitative information, qualitative analysis. It's the identity. And the amplitude, the amplitude, it's the quantity absorbed of the waves, give the quantitative analysis. It's the amounts. Here it's represented an apparatus using a filter apparatus, a mid-infrared filter apparatus. In this type of apparatus, we use a wave, but at a very known frequency. It depends on the apparatus, but there are some who use this frequency and other this one, using different filter. And at this frequency, we can detect the CH bonds, and it's to predict the fat in the milk. And if you use the other one, the nitrogen and H atoms, at this frequency, we are able to predict protein. It's an old technique used since the 60s. But the problem, we need to have an apparatus or a filter different from each type of bonds that you want to detect. And since 20 years now, we had now what we call a mid-FTIR apparatus. It's a transformé Fourier apparatus. And this apparatus has the capacity to measure the whole wavelength of the mid-infrared at the same times. And you are able to measure the absorbance at all these wavelengths. And you have, for example, the absorbance of the wavelengths 1 to wavelengths 1000. Because the mid-infrared is about 1000 wavelengths. And when you have this wavelength, all these absorbance at all wavelengths, you are able to design what we call a spectra. This is a spectra, a mid-infrared spectra. And as you can see, we can find the wavelength of the fat in the spectra, but also the wavelength of the protein at the same time. And the machines that we had in the milking laboratories at this stage, it's a black box. They use this spectra, but you never seen this spectra. What is done, it's in the spectra is measured, and they used different parts of the spectra to predict, with models in this machine, to predict some parameters related with the composition of the milk, like fat, protein, urea, and lactose. It's used in routine, in general, to predict the composition for the payment of the milk, but also for the milk, the milk recording. This technique is very fast and cheap. This is the classic use of this apparatus. But now, yes, and in general, we have three brands of apparatus. I don't know if you know, but you have what we call the Milkoscan. It's from Foss. We have also the Derespect from Bentley and the Delta Instruments. The Delta Instruments is the lactoscope. But now, this was the classic use. Now, we had a new use of these techniques. We tried to extract, since 15 years, we tried to extract the raw information of the apparatus, the spectra, in reality. We do a standardization, but I will explain more in detail after what it's really the standardization. And we try to create, to build new models. It's always new equation using different part of the absorbance spectra, and we try to predict some new parameters. To do that, we need to have access to the spectra. And to build the model, what we need is the spectra, as I said, but also we need to have reference values. It means really a measurement of a new phenotype that we want to predict. It could be a protein, methane, BHB. It's some examples here. And also we can add, if we want, to the spectra some information that we have easily. It's, for example, the days in milk or the milk yield and so on. If you have this information and that you add to the spectra, you can use it in your models. And at the end, we will have a calibration models. That's the idea. The idea after that, when you have these new models, you need to validate your models by using these models with the spectra to predict, to have some prediction, and you can compare with some results to validate your models. That's the global use. And to create these models, we need to have a statistical techniques. That's what we call chemometrics. Because chemometrics, it's the chemical discipline that use mathematics and statistical methods for the imitation of the optimal way of relevant information on material systems. To be more in detail in these techniques, okay, what we, as explained, I need the spectra and the reference analysis, and I will use these chemometrics tools to have these new models. But also I need to add some new reference analysis each time to upgrade my models. And the methodology of the chemometrics that we used are used during the sample selection. We use chemometric to select the spectra. We also use chemometric and statistics to explore our data, because sometimes we need to detect the outlier. Sometimes the measurement is not good, and we need to select these outliers and to put it because we don't need to use these outliers. And we, as you can see, we use different pre-treatment and also different techniques of the chemometrics. It's the principal component analysis. But also for we need to build the model. We also use chemometrics. I go more in detail after. And also we need to validate these models again. This is the techniques that we use. I will not go in details because we have a lot of different techniques in chemometrics to be able to predict and to create models. We have, but just to show to you, this multivariate analysis could be unsupervised or supervised. For unsupervised method, we use PCA or cluster analysis. And for supervised, we can use regression or discrimination. It depends on the parameter that we want to predict. And as you can see, in regression, we have a lot of different models. We can use multiple linear regression, or very known, it's the PCR, principal component regression. A very known and very used in spectroscopy is the PLS, the partial least squares method. We also sometimes use ANN or supervector machines, and sometimes we have some local techniques. And for the discrimination, we use these all different models. For example, PLS discriminant analysis or supervector machine, SVM. I will not go in detail to these models because it took time to explain all these models and all these techniques. But what I want there are something that I want to insist. It's how to evaluate models. When you have models, how it's possible to evaluate these models. It's by regarding some statistics, and some very important statistics. It's the first one is to evaluate the error of the models by using the root mean square error of prediction. And a second statistic very used, it's how the model fit with the real value by using simply the R square. And the third statistic that is also used to evaluate a model is what we call the RPD. It's the ratio performance on deviation. And this RPD, it's the standard deviation of your models, and the ratio of the standard deviation on the error of the model, the root mean square error of your model. And by this RPD, you have a direct evaluation of how your models works. For example, if you have an RPD of 2, it means that you can create two groups. If this RPD is 10, for example, it means that you are able, by these techniques, to separate, for example, for 10 groups, 10 different groups. For example, when you use these techniques, the mid-infrared techniques, in general, the RPD is for about 40. It means that you are able, by using these techniques to predict the fat, the total fat of the milk, you are able to create the 40 different groups. It means that this technique is very precise, very, very precise. Some evaluation and some, it's an example of how to look to this different statistic. Here it's represented some models, some equation. In general, you have in first part the parameter that you want to predict. In this example, it's, for example, the total of saturated fatty acid. Or you have also the total monounsaturated fatty acid, and so on, as you can see. Always you need to have the units used by your model. Here it's represented the mean of the models that you have and the standard deviation of your model. By using these means and the standard deviation, you have the ability to see the range of your models. Another thing is the standard error of the calibration. It gives the precision of your calibration. And another statistic is the R square. It's the R square. After that, in general, you have some other statistic giving the information about the validation. In this case, it's cross-validation that we used. A cross-validation with a standard error of cross-validation, an R square of cross-validation, and finally the RPD. And in this example, for example, the total saturated fatty acid, we are able to separate the different milk in 10 different groups. It means that it's a very precise models. It's very precise, and it's as precise as the reference values in this case. When you have an RPD of between 5 and 6.5, it's a good models, it's a quality control, and so on. You decrease all the time the precision and the ability of the application of these models. For example, between 0 and 2, it's very poor. You only allows to compare groups of score, distinguishing high and low values, but it's very raw. But one thing for geneticists which is important, it's even if you have an RPD with a low value, it could be interesting, because if you are able to use a model on a very, very large data set, and it's what we do generally with the milking with the milk, we are able to predict a lot of spectra on different individual cow. And what is important, it's with low statistics models, we are able to predict a lot of data, and even if it's poor, it gives to us a result. I'm not very clear. This is the end of the first part. I don't know if you have some question related to this introduction to the mid-infrared. Please ask me if I'm not clear.
Just regarding the basics of spectra information, we're focusing on the mid-infrared part. What about the lower and the upper infrared? Can you comment on that? I'll be very pleased if I know really why focus on the mid-infrared rather than the uppers and also the lower infrareds. That's one question. And the other is on the spectral graph. There are also values below the threshold. What do those values below the threshold refer, and how can we interpret or understand those values? And my third question is, you have shown us a list of models, the PLS and so on. So which one is most appropriate and frequently used for the application of this information to evaluate and predict whatever you want to predict with the milk or other types of data?
For example, we have
your first question is
the
difference between near infrared and mid infrared.
Yes. What we need to to take into account, when you use spectroscopy for milk, in general, it's mid-infrared, because in general, this technique is more dedicated to liquid samples. You need to take in mind that for the near-infrared, for example, this technique is very used with solid samples. For feed ration, for example, all the time it's the near-infrared who is used. It's a little bit complicated to explain why, but you need to. It depends of the energy of the waves, because the mid-infrared we have a lower energy, and it means that you have you need to use very thin cell by using the mid-infrared. very thin cells means that you have a very thin part
In general,
of the samples
you need to have
who can be measured.
samples without
Okay.
water.
When we say thin, it's very thin. It's a micrometers length of the cell. But for the near infrared, as you have more energy in your waves, you are able to measure larger samples. For example, we have cell of around 1 centimeter. It can be used, and for the solid, it helps us to measure these samples, these solid samples. Also, they are the interaction of the water who doesn't help the near infrared. You can retain this. In general, you need to have samples without water by using the near infrared. The theory of the near infrared is different from the theory of the mid infrared. What I explained with the springs between the bonds and so on, it's for the mid infrared. For the near infrared, it's another idea. It's not exactly the same theory. Okay? That's why we need to use different techniques for the liquid and the near infrared and the solid. But near infrared sometimes could be used for liquid. We use near infrared for the milk sometimes, but the precision of this method it's lower than the mid infrared. That's why in routine we use this mid infrared techniques in the milking labs and for the payment and so on. And the precision are very better with the infrared technique.
But
The second question was okay. Just to show to you. Yes, here it's a spectra. Huh? And sometimes you say to me, oh, you have negative absorbance. Yes, that's true. That's why, in general, the first step that we make it's a pre-treatment. We make a pre-treatment to change this negative information in positive information. Okay?
So meaning that we do a kind of transformation?
Yes. Yes. We make a transformation, simple transformation. What we will do also, in the spectra, every wavelength it's not necessary and it's not usable. For example, in the spectra, there are a big part of noise due to the interaction with the water, and it's a very noisy part. And in this pre-treatment step, we put away this noisy part.
How did you determine the threshold itself? I saw in one of the graphs I saw a kind of horizontal line, and I took it as a threshold.
It's a zero.
Okay.
It's an absorbance. Huh? It depends of the apparatus. Sometimes it gives to us the transmission and sometimes the absorbance. But it's the lower part is zero and the upper part it's 100. It's an absorbance. Okay. And the third question was.
Among the models which one is frequently used in the models you have listed.
Oh yes. I have no answer to your question. You need to test a lot of models. There are no simple answer. Yes, you can, when you want to create a models, for example, to discriminate, you only use this type of of techniques. But when you want to quantify something, you use this type of techniques. But which one is the better? There is no answer. It depends really of what you want to predict. There is no really an answer to that. That's our job. It's to find the way to have this better prediction. Okay? Any other questions related to this introduction to mid-infrared? I know that some people are aware of these techniques and some knows nothing on these techniques. It's important to understand these techniques to continue in this presentation.
Only one comment about the MIR and the myth. You say that MIR is used in milk analysis. I think it's a matter of concentration of the components that you are analyzing. In fact, in robots, you can use MIR to determine the percentage of fat and protein. But if you need to analyze very low concentration, for register or something like that, I'm not sure.
Yes, it's related to the fact that the near infrared is less precise than mid infrared, and if you want to be more precise, an idea is to concentrate by, for example, the powder. When you compare the measurements of a sampling powder of milk to a liquid milk, the precision will be better with the powder milk than the liquid milk, because you concentrate in reality your matrix. In the second part, I want to insist on two topics. The first one is about the robustness of a model, and the second one is related to the standardization. I had a small. I introduced in the first part the standardization. We will see why it's important to use the standardization process when you want to create a new parameters. The first one is about the robustness. What is the robustness? In reality, it's the potential of a models, of your models, to provide good results in all the conditions. What it means in all conditions? It's on all the milk that you will measure, your models need to work. That's normal. For example, also, your models need to work with all the deeds of the cows, of the feed used in general. If it works well with every feed, it means that your model is robust. But also, as you are geneticists, for the main part of you, it's important to have a model who can be used on every breed. And also, for the persons who works in different labs, it's important to have a model who are able to work with all the brands models and all the instruments. We need to have all-terrain models. For example, here, when you cover here it's represented the reference data range. You have the reference value, and we create models in one country, for example in Belgium. And if we want to predict in another country, sometimes we have this type of results. It means that our models doesn't cover this variability. It's a it doesn't work. In general, you can say, okay, I have a model very linear. I'm sure that it works in this country. It's in the other country, but no. In reality, you need to add this information, this new information for another country in your models. You need to enlarge the variability of your models. That's very, very important. When you want to create a new model, the first step is to be sure that the variability of your models is very, very, very large. And to do that, we need to collapse different samples coming from different countries. That's a way. In this example, we used reference from another country who cover this variability, and by upgrading our first model by using the different reference analysis of a new country, we enlarge our variability and we increase our robustness. An important thing, it's very difficult to develop a robust models in only one country, because in general we have not the whole variability in only one country. That's why it's very important to build a model with good collaboration between countries. The international collaboration is needed. And the different data set cover complementary variability. An example is represented here. It's a model that we create to predict the methane emission by the cows. In the very beginning, we only used results from Belgium, from the Wallon region part. And we try to create and to organize different experiments to enlarge our variability. But what we saw by using different reference analysis coming from another country, from Ireland, we saw that we don't cover, in reality, the whole range. We discovered that in Ireland we had cows with lower emission of methane, due to the fact they used a lot of pasture in this country and so on, and also they use a different breed and so on. And that's why it's very important to organize an international collaboration to enlarge this variability. And now we exchange with a lot of different partners to be sure that the robustness of our model is done, is increased. It gives to us the idea of the robustness related with the reference analysis, but take in mind that sometimes, for example, a spectra of a milk give to you, for example, 4% of fat, but another one, exactly the same, another spectra, very different, give exactly the same reference analysis. 4% of fat. It means that we need also to cover the old variability in the spectra, because there are some relationship in the spectra who can be different, and we give to you exactly the same reference analysis, and you need to cover this variability. Here it's represented the country 1, and it's another samples, and we can consider that we more or less cover the variability in the spectra, but we need to add also the spectral variability by using different milk, and the conclusion are exactly the same. You need to enlarge our models by covering different reference analysis, but also different type of spectra. There are a lot of things, a lot of parameters who influence the robustness. We need to cover the different breeds, feeding system, and geographic origin, but also we need to integrate the different brands, the different instruments, instruments in our models. An important thing also, pay attention to the precision of your reference analysis. the precision of your reference analysis, you can evaluate it by using the standard error of the laboratory. It gives to you the precision of your reference analysis. And if you have a precision standard error of the laboratory very low, pay attention that it will have an influence on your models. In fact, the R² maximum that you will have depends on this standard error of the laboratory. Lower is the precision of your reference analysis. Lower R² you will have in maximum. It's more difficult to have an R², a good R², if you have a bad reference analysis precision. This is important. And also, when you want to create models, you need to avoid overfitting when you use your model. Overfitting is to use a lot of information, a lot of PC numbers in your models, but it's more in detail here, but pay attention to that. A second point, it's about the standardization. As I said, to increase our robustness, we need to enlarge our data set of reference analysis by exchanging between the different countries, the different experimental farms, the different breeds, and so on. And what we do in general when we collaborate with new partners to exchange this reference data, we create a collaboration, we create a network, and we exchange spectra from different countries who use different instruments. The instruments are not the same, but sometimes they use different models, different brands of instruments. And it's a problem. We will see why. Different instruments means that you can have difference if you measure exactly the same milk with two instruments. In reality, you will not obtain exactly the same spectra. And it's just because the spectra will depend on the temperature and the humidity of the labs. If we are in Spain and in Belgium, and you measure exactly the same samples, it will change because the apparatus is very influenced by this temperature and humidity. Also, sometimes you change a piece in your apparatus, and we can see that this change of piece have an influence on the spectra. In reality, here it's represented. We use for that to create these figures. We use during 6 months the spectra, the raw spectra, without any calibration or something like that. You just use the raw spectra, and we use the models of prediction of the fat. And here we saw that we have a big change in the fat prediction. And for this example, we use always the same milk. It's in reality an UHT milk used to be sure that we have exactly the same milk, and we saw this. And it's when we go back to the labs, we exchange with them, and they said to me, "Oh, we just have a piece replacement," and we can see this. This problem on this graph. The maintenance operations is very important, and also the wear of the apparatus is important. The cell, in reality, the cell, when you use it, as you measure and measure and measure a lot of you use it, and we can see a small deviation day to day due to this wear. And also, as I said before, the instrument could be different. We use different brands, different models. Here is represented the PCA of the spectra of informative wave number for 5 common samples measured with 45 instruments from the same brand. It's a representation of the variability, the spectral variability that we have when you measure exactly the same samples in different labs on different apparatus. As you can see, for here, for example, it's one apparatus in red in one country. Here, it's another one in another country. As you can see, the spectra given by these different apparatus are not exactly the same. And it's important. For example, if we use these 5 common samples and we measure on a first apparatus, here it's a FOS apparatus that we call FOS1, another one it's the delta 1, and here it's represented the spectra. As you can see, it looks totally different. And when you want to use a model, a common model on this spectra, as you can see, here it's the methane models, and you use it on the FOS models. With these FOS models, it was the apparatus that we used to create these models. And as you can see, it works well. It works well. But if you want to predict on the delta instruments, it's impossible to use it. We have error. It doesn't work. The representation, it's like that. If we want to compare the delta prediction to the FOS prediction, we have nothing. It means that it's not possible to use a common models on 2 instruments from 2 brands. It's good to know. But you will say to me, oh yes, because you use a different brand apparatus. And a constructor will say, oh, my model only works on my instruments. You need to use a FOS apparatus. Okay, we will try. Here it's represented 2 FOS apparatus, FOS1 and FOS2. It was exactly the same samples, 5 samples. And yes, it's true. The spectra seems to be similar. Seems. Because if you pay attention, sometimes we have some part, very thin differences, but it's important. Because when you want to use the same models on these 2 apparatus, the first one is the same, exactly the same result than previously. And the second one, as you can see, the error of the first two, it's too large. It means that when you compare the first 2 and the first 1 prediction, it doesn't work. It means that it's not possible to use a common models on 2 apparatus of the same brand. That's a problem. But it's a known problem. It's a known problem for the persons who works in with mid-infrared apparatus. In general, what we do because it's due to the fact that you have different apparatus, and you need to make a correction to your spectra. And in reality, what is done with some components like fat, protein, lactose, urea, in general, in all the labs in the world, they use what we call classical slope bias correction. And to do that, they always measure samples by using the reference analysis, and they made a correction by slope and bias. It's what we call the correction. It's a I search a word. I will go back. It's a calibration, what we call calibration. Okay. But it's you can use it also for new models like fatty acid, because in reality the fatty acid is really the fatty acid that you have in your milk, and you are able to measure fatty acid by using GC reference method, and you create a data set and you are able to correct the value. But as I said, we have new parameters that we want to create. And in this new parameter, we have also parameters that we call indirect parameter. It's a milk indirect relationship. For example, we are able to create models to predict the minerals, the major minerals, calcium. We are able to create calcium to predict calcium in the milk. But in reality, the calcium, it's not an organic bond. It's an indirect relationship that we have. It's the calcium, it's not really the calcium that we predict. It's an indirect relationship. Or for example, the BHB, the beta hydroxybutyrate in the milk, the concentration are very, very, very low. And in reality, it's not the BHB concentration that we are able to predict. It's the relationship, the existing relationship with other component of the milk that we predict. It's a milk indirect parameters. We have also models created by using reference analysis done not directly on the milk, but on the blood. For example, for the BHB and the NIFA, we measure these parameters on the blood. We use the spectra of the milk, and we are able to predict BHB and NIFA. You can imagine that it's impossible to use milk to change the calibration. And a last group, it's the models that we call the models depending on the phenotype measured. For example, it's the methane and the body energy status. The methane, in reality, it's not the methane that you measure, because the methane is the emission by the cow of the gas. It's not in reality the concentration of the methane in the milk. That's why we need to create another solution to answer to this question of change of spectra and relationship and calibration. It's impossible to calibrate with these parameters. That's why we find another solution that we called standardization. It was done during a project called MIR. And in this project, we don't want to calibrate and to change by correction and bias and slope changes. But what we've done, it's directly to harmonize the spectra in a common format. By using this method, we are able to merge data, to create common models, to use these models on all the instruments, to stabilize the instruments in time, and also we are able to share technical and financial resources, because when you want to measure, for example, the methane, it's very expensive to measure by reference analysis, and by sharing this data, you decrease your cost. But what is the principle of the standardization? Just a representation to understand. Here's the variability in spectra represented for the different brands, for example, and you have Here it's for the different instruments in the brand. Another one, it's the brand 2, it's another distribution, and the third one, it's another one. In reality, what we do, we select instruments in one brand that we call masters, and we create a master. We harmonize the spectra, and we use the spectra of these these numbers of apparatus, and we use these spectra to harmonize on the common format for the whole apparatus. And by using this, after that, we have the common format, and we are able to standardize the instruments for creation of new equation, and we are also we are able to use for the standardized instrument to use this new equation. How it works in reality, the standardization, it's described in these two papers. These two papers were published by Clément Grelet in 2015 and in 2017. If you want to have more detail, please read these papers. But how it works in reality? In reality, we use 5 common samples that we distribute to the all labs. For the moment, we have more than 100 apparatus in 41 labs, and we distribute these these samples in all the labs, everywhere. And after that, we correct we harmonize the spectra by using a method that we called piecewise direct standardization, a PDS method. I will not explain more in detail this method, but just to show to you the results. In reality, it's the same figures than the previous one. Here in blue, it's the unstandardized spectra. When here it's the representation of the master, or the 5 apparatus. And the master is the spectra master. Here it's the slave spectra. And after that, we standardize by using the PDS-wise method. And we, as you can see, the variability, the spectral variability decreases a lot by using this method. And we need to repeat this method each month. Each month, we distribute these samples everywhere in the 41 labs, and we recalculate each time new coefficient. For every absorbance, we have a coefficient who is able to correct the spectra to be sure that at the end, after the standardization process, we have exactly the same spectra for the same samples. And now, it was the figures for the two first apparatus using unequal models. And you remind that it doesn't work without standardization. And now, if you want to use if you use a standardization process, you can see here that it decreases a lot our root mean square error from 200 in this case to 20. It decreases a lot this problem and decrease the precision. It means that now it's possible to use the common models on 2 instruments from the same brand. And what happens with we want to use 2 different brand models, because it's important also. Huh? It was the representation of before, and now you can see that we had a root mean square error of more than 700, and we decreased this root mean square error at the same level than before, around 20. We have exactly the same results by using different spectra from different brand instruments. That means that we are now able to use models, common models, on this different brand apparatus. And in routine, it's what we do now. During the mean control, the apparatus use the mid-infrared. We exchange the spectra. We create big data set. We harmonize, we standardize the spectra before, and now we are able to use new models, and new models who are not able to calibrate, new models, and now we are able to predict new phenotypes like ketosis, risk, methane, and so on, and also models that I will present in the third part. In conclusion, it's very important to use a common language between the instruments because it allows international exchange. It's important if we want to share data and models, and also to create robust common models. And if we want to use the same models on all the instruments, we need to standardize. And also, it's a last point, but for the geneticists, it's very important. Now we are able to create a spectral database, because, as I said, the standardization, we do the standardization each month. It means that you can build historical database. In Belgium, we had used the standardization process since 2012 or 11, I don't know. And now we have a big database, and we are able to use it for the geneticist, because we are sure that the spectra of 10 years ago are the same that now. And we are able to predict some new models on spectra from a cow who is not still alive. That's the advantage of this standardization. It finished the second part. I don't know if you have questions.
Thank you very much. If you calibrate the equipment in the master collection, because if I understand what you explained, your calibration for all the between labs, it's only valid for a particular moment, no? Because if the conditions of the equipment in the master collection change over time, calibrations will be different.
Yes.
Calibrate over time.
Yes. The idea, you create coefficient in a fixed moment during a period, and when you build your database, you still take into account the fact that you need to use the coefficient of calibration of the moment that you measure the spectra. You don't need to use the new coefficient to use it on the old spectra. It's only for the spectra that you use at the moment that you measure. Do you understand?
Yeah, but if you want to work in an experiment that you have measures over time in different moments, I think that you should try to standardize all the measures for the condition at the beginning in the master collection, Is that right or not?
Yes, but it's not important. For example, if your experiment starts at the month 1, and you measure at the month 2 and month 3 and month 4, you need to correct your coefficient by using the coefficient created in the month 1 for the samples of the month 1, and the coefficient of the month 2 for the month 2, and the month 3, and so on.
For that, you need to use the same samples that you used in the first time?
No.
No?
No. No.
And what happens if the conditions of the equipment change? If the same equipment?
Yes, but it's in reality it's more complex than what I explained. But in reality, we check by using other things. I don't explain everything. By using other things, we check if the apparatus that we use for the creation of the master have not changed. Okay. Now it's the part 3. It's more on the models that we have created during the GplusE models. It's I will show to you 2 examples of the models. Some examples of models related to the metabolic status prediction and also to the nitrogen efficiency. The first one, it's works done by Clément, and it's directly related with the objective of the project. The idea is to, in the final step of the project, it's to use GWAS and also to make some experiments in the management study. But the first step of the project, the GplusE project, it's to create models, to create proxies related to the milk glycan metabolites, but with mid-infrared spectra. Why mid-infrared spectra? Because it's very cheap and you can use it everywhere. In general, all the country have these own instruments, mid-infrared instruments, and it's still used in the milk recording system. And in general, we have relationship with the genotypes and so on. That's why we want to use this method. We search different parameters related to the energy and metabolism status, because due to the relationship that these parameters have with the fertility and the health, that's why we search this type of parameters. We have created different models by using different reference analysis. Here is represented the 3 different parameters that we used. The first one was feed-related phenotypes. The second one was reference analysis using blood samples that we sampling during the different experiments. And the third one will give you a global metabolic status using a clustering methodology. I will explain the three in this material and methods. For the first one, this is the experiment that we organized in the GplusE project. We have 6 experimental farms who measure on 241 cows, and by using a common sampling protocol, we measure on Holstein by using only one breed. It's a problem, but we have only one breed in this experimental design, and we measure during between the calving and the days in mill 50. It's short. It doesn't cover the whole lactation period, but that's the reference that we had. Sometimes we need to follow what is done. And you can see also that we, in all these experiments, depending of the country, we use different feeding system with grass, corn silage, critical, and so on. And also we cover another one variability. I didn't speak about that, but you also need to be sure that your models works on primipar and multipar. It depends of the parity. And it's good here, we have a good distribution. Alors, yes, for the feed-related phenotypes, we measure the energy balance. We measure the residual feed intake, and we measure the dry matter intake. We make this all measurement daily during these 15 days. And for the dry matter intake, we only measure this dry matter intake daily in 3 farms. It was not possible to do this measure in the 6th farm. Okay. For the second type of parameter for the blood plasma metabolism and hormones, what we measure in the blood, it was the concentration of the glucose due to this relationship with the energy. The IGF-1 due to this relationship with the liver status. The NIFA, it's an important parameter that we measure in blood to follow the mobilization. And the BHB, it's to detect if we are in presence of ketosis or not. For the blood measurement, we did the measurements 2 times, at the 14 days and at the 35 days. And we make the sampling in the whole farm, and we measure this reference analysis in 2 labs, 2 different labs, in Dublin and in Aarhus. And for the phenotypes of interest, the blood metabolites and hormone, we think that it's, in general, it's important to use it not separately, but in general, you can imagine that it's important to have the global parameters together. That's why we try in the 3rd part. We try to create a cluster solution, and in this cluster solution, we try to create combination of blood metabolites and hormones in 2 different groups. It's represented here. We have 3 different groups with healthy, intermediate, and co that we called who are not healthy, who detect a problem, and we create these 3 different clusters. For the MIR analysis, the analysis was done locally or in the CRW. We measure twice per week. We measure also during the milking of the morning and the evening. And what we did, we make a weighted average of the spectra depending of the milk production to create a spectra, a daily spectra. And we use 2 brand instruments. We use the standardization. I will not show more in detail this. The advantage is when as we will create a common model, we will be able to use these models everywhere where the standardization process is used. Okay, for the results, here it's represented the different spectra that we had. Here it's after standardization, the PCA of our data set. It's just to show to you that we had a good standardization procedure with not a lot of difference between the different farm. In general, we have the same type of spectra. It's important for us. A fourth model that we create is the dry matter intake models. We use for that the mid-infrared spectra, but also we had to the spectra the information related to the days in milk, and also the fat corrected and protein corrected milk. We had this information because we have this information in general and routine, and we use this information. In these models, we use the PLS, and the results are given here. We obtain an R-square of 0.6 and a root mean square error of 2.8. It's not very good results, but it's usable results. And for the other one, for the energy balance and residual feed intake, as you can see also, here is represented different model that we create only by using mid-infrared and also by using days in milk and the fat and protein corrected milk. But as you can see, each time it's better when you use more information to you add information to your spectra. But as you can see, these results are not very, very good, but it could be used if you predict it on a large database. And another group of predictions, it's based on the metabolites measured in the blood. And here we have very interesting results, not for glucose and NIFA prediction, but as you can see, we have good results for the BHB and the IGF-1 metabolite in the blood. We are able to predict relatively with good statistics these parameters. And it's important, for example, if you look in this graph, this is the representation of the measured blood BHB and the predicted blood BHB. As you can see, with an R-square of 0.7, it looks not very precise, but if we use a threshold of 1.2, we have an accuracy of a global accuracy of 92%. It means that we are able to classify with a relatively good precision of 92%. It means that we can use it in routine to try to detect the BHB. It's for the ketosis detection. We are able to use these models to detect cows with potential problem of ketosis. And the last point is related to the clusters. As I said to you, when you look to the metabolites in the blood, okay, it's important to have the BHB. You can look for the BHB only. No, the important is to be aware, to have the information if a cow is healthy or not. And to do that, you need to have models, tools who is able to detect a lot of potential problem, healthy problem. And as you can see, we have created 3 different groups who use different glucose, IGF-1, NIFA, and BHB. And in general, the first group give information about healthy cows, the second one intermediate cows, and the third one it's imbalanced cows. And if we want to use this model to predict the energy status of the cluster, we can see that we are able to detect 45% of good classification. But only 4% of our results show that only 4% of our prediction give to us a misclassification. We say that we predict that you have an healthy cow, and this cow is, due to the results that we measure, it seems that it's a sick cow. But it's only 4%. And now if we can also only use intermediate and healthy cows in the same group, and we are able in this case to have a global accuracy of 87%. You can find this all details in a new publication of Clément of this year. And what is important, it's that it seems that we can create different models on energy status, but we need to validate all these models. We need to have in the future a validation step. But we can imagine that we imagine that we can use these models to predict results to be used in genomics. The last point that I want to present to you is the models that we have created, and it's very first models to create models related to nitrogen efficiency. It's a very first approach. In reality, we used the first results to create a first approach to see if we are able or not to predict this nitrogen deficiency. And it's important, the nitrogen deficiency, because it's as you know, the cost of the protein is very important for in dairy production. A poor nitrogen deficiency is affecting the profitability of the farm. Also, nitrogen have a big importance on environmental impact due to this relationship with ammonia and oxides emission, and also due to the leaching in water resource, what we call eutrophication. Also, nitrogen efficiency have a potential negative impact on reproductive performances, and also have a potential negative impact on the milk processing quality for the cheese making ability of the milk. Okay, as you know, nitrogen in milk is easy to measure. We always measure protein with mid-infrared spectra, but to predict the potential presence of nitrogen in feed, we need to. That's the part that we need to test. To create these models, we use data from 3 farms in UK, Denmark, and Ireland. It's only 136 cows, and it's exactly the same experimental design that before. It's only Holstein, and it's only we cover only the very beginning of the lactation period. We measure the dry matter intake daily, and we smooth in 3 days. We feed the feed composition also. It's analyzed weekly. The milk production recorded daily, and also an important fact in this experimental design, we have no idea of the urine production and urine data, and also we have no idea of the feces data. It's important. As I said, it's an experimental design just to check if there is a potential to use it. We have no built this experimental design to have a final models. As I said, we have no information in urine and feces, and as we have no this information, maybe the efficiency potentially maybe we overestimate potentially the efficiency. It means that we underestimated the losses of nitrogen. We need to be aware of that, but we don't. It's impossible. It's impossible for us to change nothing about that. Okay, the spectra are taken exactly in the same condition than previously. And for the mid-infrared calibration, we have no removing of outliers. We use, in this case, predictors, the spectra. We had the parity and the milk yield. To validate our models, we use two different procedures. We use the cross-validation procedure, and we use also the external cause validation. Here it's represented our results. It's a descriptive statistics of our results. As you can see here, the nitrogen efficiency distribution is very, very large, very large. And if we compare these results to the literature, it seems that we have very large, more large variability. We explain this extreme data. We explain this because we have, in our case, individual data compared to the literature, who they only use Earth data. If you use individual data, you enlarge your variability. Maybe it's it explains why we have this so large variability. And also we see that we had some very high efficiency. Maybe it's explained because we are, as I said, we are in the very beginning of the lactation period. And maybe it explains why we have this high efficiency results. Because we know, and it's represented here, if you look to the efficiency during the days in milk and the lactation, you can see that in general, the nitrogen efficiency, it's higher in the beginning than in the second part. Also, some descriptive statistics show to us that our result, our nitrogen efficiency are related with the milk yield. That's normal. It seems, when we compare our result with the literature, it's totally normal. Also, we have a relationship between the nitrogen in milk and the nitrogen efficiency. That's normal too. It's weighted. Here it's represented the nitrogen intake relationship. It's a negative relationship with the nitrogen efficiency. It's also weighted. Here it's the crude protein in the feed. As you can see, with larger crude protein percentage in the feed, we have a lower efficiency. It's normal. And finally, it's the representation of the energy balance with the nitrogen efficiency, and we have a good relationship between, a negative relationship. Also, it's weighted. Okay. And what about the models? And I will conclude by this. What about the model? For the two models that we had created, we had a first model, it's the nitrogen efficiency. As you can see, we can see the last here, it's the best one that we had. It's by using the spectral vector machine method, and by adding the parity and the milk yield, we had an R square or cross validation of 0.74, and it's represented here. It seems that it works well. It's possibly, it showed to us that the mid-infrared could potentially predict the nitrogen efficiency. It's the first time that we see that we are able to predict this, and it's important because it seems that we are able to predict the nitrogen efficiency. Here it's the result given by another validation. It's not in cross-validation, but in external co-validation. And our models show that in general, our results are good. The performance are still good for the cows. It confirms the potential of the models. And the last models that I want to present today, it's the nitrogen losses. And as you can see, the last models here have also relatively good results. And it seems that it's also possible to estimate the nitrogen losses with fair error. But as said, it's the very first results. We need to confirm this study. We need to validate our models, and we need to exchange a lot of data because we are at the very beginning of these models. But it seems that we have some possibility to predict these types of nitrogen losses and efficiency. I just remind in my conclusion that the robustness needs to be increased by exchanging data. That's important because at this stage, the models that we created, we couldn't imagine that these models could be distributed everywhere, and we are not able to say, oh, it works. No, it's first results. We need to continue the works. But we can use it to test the genomics. That's in research, it could be done. And also an important last point, if we want to be more, to understand more in detail this first model, we need to take the nitrogen and the energy balance into, we need to take into account in our models. And to do that, we need to measure the faces, nitrogen losses, and urine nitrogen losses. Okay, it's finished my presentation. If you want, in the future, one more trained in the modeling and also in chemometrics, we organize each year a training in our department, and the next year it will be in March. You have all the information here. Just write the address, the email address of my colleague Juan Fernandez. It's a very interesting training because after that normally you are more or less able to create your own models, and that's the idea by using some modeling approach, different modeling approach. Okay, thank you very much.